Assalamualaikum and hello everyone. My name is Muhammad Afiq Fikri bin Muhammad Aziz from Sanyo. This video is part of our electrical technology course and I'll be presenting job sheet 6. In this job sheet, we explore the simulation and analysis of delta star and star delta transformer connection using MATLAB Simulink. Let's begin. Before we jump into the task, let's take a moment to understand the two types of transformer configuration. A delta star connection is used to step down voltage and to create a neutral point for grounding, making it suitable for distribution system. On the other hand, a star delta connection is useful for stepping up voltage and reducing inrush current in motor starting application. These setups are widely used in industrial and power distribution networks and is a key to maintaining voltage stability. In Task A, we focus on delta star transformer setup. Here, the primary side is connected in delta and the secondary side is star. This configuration was simulated in two scenarios, one with a balanced load and another with an unbalanced load. The goal was to observe how the voltage and current behave under both conditions. The balanced load setup involved equal resistor in all three phases. In the simulation, we used both phase-to-phase and phase-to-ground connection. The readings show consistent values across all phases, approximately 59.37 volts and 0.004947 amperes. This confirmed that the system was balanced with symmetrical voltage and current distributions. In the second part of Task A, we simulated the same delta star transformer, but this time using a phase-to-ground connection. Here, each load was connected from one phase directly to the neutral point or ground. This is a typical setup in star-connected system, especially when we need a niche reference or when grounding is required for safety. Again, the load were balanced with equal resistance values assigned to each phase. The simulation measured voltage is 59.37, just like face to face. And that also applies to voltage and currents, which have the same value. The readings were identical to those in face to face scenario because that indicates that the transformer provided consistent performance and the system maintained electrical balance. This type of connection is particularly important in residential or commercial power system where grounded neutrals help stabilize voltage and protect equipment. Next, we simulated an unbalanced load by using different resistor values in each phase. The voltages remained steady, but the currents varied between phases. This imbalance is common in real-life applications and can cause system instability if not managed properly. From Task A, we saw how balanced load result in uniform currents and voltages, ensuring efficient operation. In contrast, unbalanced loads lead to current variations, which are critical to monitor in real applications. Understanding this behavior helps prevent energy loss and maintain system stability. In Task B, we examined the star-delta transformers setup. The source was star-connected while the load was in delta. Each phase of a delta-connected load had a resistance of 12,000 ohms. This setup is commonly used in motor starting systems to limit inrush current and protect components. After completing the setup for star-delta connection in Task B, we ran the simulation to observe how voltage and current behave under a balanced load condition. In this configuration, the primary side of the transformer was connected in star and the secondary side in delta. The load on the delta side consisted of three resistors, each with a resistance value of 12,000 ohms. This type of load is symmetrical, meaning it is equally distributed across all three phases. During the simulation, we measured several key parameters, which is line voltage, line current, and also phase current. Let's go through each of them. First up, we have line and phase voltages. The line voltages, which is the voltage between any two of the three lines, was measured at 178.1 volts. This high voltage is expected in a delta configuration where the phase voltage and the line voltage differ based on the square root of the ratio. The phase voltage, which is the voltage across each resistor in the delta load. came out to be 102.86 volts. This confirms that the load is properly receiving the required operating voltage per phase. This result follows the standard formula for a delta load, which is V phase equals to V line over square root 3. So 178.1 volt over square root 3 equals to 102.86 volt, which validates our simulation accuracy. Now, looking at the current readings, the line current, which is the current flowing from the source into each line, was 0.0257 amperes. For the phase current, which flows through each resistor in the delta configuration, was measured at 0.01484 amperes. In a delta system, the line current is square root 3 times the phase current. This is confirmed by current line equals to square root 3 times current phase, which is 0.01484 amperes times square root 3, which equals to 0.0257 amperes. Again, this may show that the system is operating as expected under balanced load conditions. Now for the power and balance, using the formula for power in a three-phase system, P equals to square root 3 times V line times current line. We can estimate the total power delivered to the load, plugging in the values square root 3 times 178.1 times 0.0247, which is 7.73 watts. This tells us that the total power consumed is relatively low due to the high resistance value, which is typical in simulation studies where the focus is on current flow and phase behavior rather than the power consumption. Most importantly, the system maintained perfect symmetry. All three phases had identical current and voltage values, proving that this star delta setup was correctly implemented and the load was balanced. So, what can we conclude from task B? We learned that the star delta systems are ideal for applications requiring stable and efficient power. They help maintain balance in industrial settings and reduce current surge during motor startup. The power was calculated using the formula P equals to I times V, which show reliable energy flow throughout the system. So here's a quick summarization. The delta star configuration is used to step down voltage and add grounding, while the star delta connection is useful for stepping up the voltage and controlling the startup current. Through this simulation, we better understand real-world transformer behavior and how balanced and unbalanced load affect system performance. And that's all from me. Thanks for listening and see you again.